Hello, everybody, and welcome to the second lecture for week 5. So today we're going to talk about quadratic numbers. I just want to make a quick note. In the class on Tuesday, I said that in the lecture we would discuss an application of this pattern you noticed in Pascal's triangle in exercise 1 in the worksheet. But actually, I'm going to delay that till a little bit later in the class. We're not going to use that pattern for anything else on the worksheet this week, and I realized it's just going to make this lecture a little too long if I included it. Okay, so well, let me make a definition. So if I have some complex number alpha, I'm going to say that number alpha is a quadratic integer if it's a root of a monic degree 2 polynomial, so something like x squared plus ax plus b. So a complex number alpha is a quadratic integer if I can find such a polynomial f of x equal x squared plus ax plus b with a and b both integers, such that f of alpha is equal to 0. Okay, and I say a complex number is a quadratic rational if the same thing is true, except maybe instead of finding a and b in integers, sort of my polynomial has coefficients in the rational numbers. So let me discuss some examples. Well, the number I, so I is a square root of -1 in complex numbers. This is a quadratic integer because what does it mean to be a square root of -1? Well, that means f of I, that means you're a root of x squared plus 1. So if I sort of take that polynomial, I plug in I get I squared plus 1, which is -1 plus 1, which is equal to 0. Okay. On the other hand, so that's a quadratic integer because this polynomial fx equals x squared plus 1 is a monic polynomial with integer coefficients. Okay. On the other hand, if I take I over 2, well, this is still going to be a quadratic rational because it's going to be a root of the polynomial x squared plus 1/4, but it's not a quadratic integer. If you think about it a little bit, you'll see that it's not possible. Even though you can find this polynomial with rational coefficients, monic polynomial with rational coefficients where f is root, it's not possible to find a degree 2 monic polynomial with integer coefficients such that I over 2 is a root. Okay, so that sort of shows you the difference between these two ideas. And I'll come back to that in a minute. And more generally, so say I start with some integer d, and then I take two other integers a and b. Well, if I look at square root of d, so look at square root of d, which is, well, this is a quadratic integer. It's a root of x squared minus d. So that's a quadratic integer. So that corresponds to sort of something of the form a plus b squared of d, where a and b are integers, and when I take sort of a equals 0 and b equals 1. But it turns out sort of any way you sort of take a multiple of square root of d and add to it a, you get a quadratic integer. So let me just sort of write down the polynomial. Turns out this is the root of x squared minus 2a x plus a squared minus b squared. Okay, so you can get this by, it's maybe a good exercise for you to see, try and get this on your own, but you get this sort of by, we can think of it by completing the square, but sort of you can use, let me just say by completing the square, and sort of think about where this comes from, and we'll come back to this formula in a minute. good, but so this is sort of some illustrative examples of quadratic integers. Which know any quadratic integer is a quadratic rational. And sort of the same thing that happened up here, I take a and b in just rational numbers now. So I take a plus b squared of d, where d is an integer. Then, so the same polynomial will still work. This will still be a root of this polynomial. What I get, what I get will be a quadratic rational. So now sort of this polynomial might only have rational coefficients, not integer coefficients, but I still get a quadratic rational. So when a and b were integers, then this is also, these coefficients were integers. So that's why in this case I got a quadratic integer. Okay, so on that note, there's an important fact that I'm not going to justify, but it's convenient to know and we'll use it. So let me just state it as a sort of fact that you can take from me. So if you have a quadratic rational number alpha, that means it satisfies some degree 2 monic polynomial. It's a root of a degree 2 monic polynomial with coefficients in Q. So if that number alpha is a quadratic rational, but it's not itself rational, so of course any rational number is a quadratic rational, because 7 is a root of x minus 7 squared, for example. But so if you're not in this case, if you have some quadratic rational that is not itself a rational number, then there's actually exactly one degree 2 monic polynomial such that f of alpha is equal to 0. And with coefficients in the rational numbers. So in particular, if I have a quadratic rational that's not rational, and I want to check whether it's a quadratic integer, then sort of as soon as I found one equation of this form, where alpha is a root, then I know that's the only one. So if I want to check if it's a quadratic integer, I have to check in that equation if whether my a and b are integers or not. Okay, so I want to make a nice observation. So we've been talking about, okay, so before now, we've been talking about rings and doing modular arithmetic in general rings. And now I'm sort of out of nowhere talking about quadratic integers and quadratic rationals. I mean, they're not completely out of nowhere. I mean, we've been talking about square roots a few times in the class. Like we talked about them when we're discussing continued fractions, for example. Well, we talked about like squares. Yeah, we talked about sort of like the equation like x squared minus 1, sort of mod p, and sort of things like this. So it's not completely out of nowhere, but to connect it sort of a little bit more firmly, I want to observe that when you start with quadratic rationals and quadratic integers, like if you can arrange them together into certain rings. So in particular, if I look at like something like a plus b times a plus b squared of d, and I multiply by c plus d squared of d. Let me just expand this out. I get ac plus b squared of, so bc squared of d. So I'm just going to FOIL it out, plus ad squared of d plus bd squared of d squared of d. If I organize the terms, well, I have AC, and then I also, like these two square root of d's, when I multiply them together, I just get d. So I get AC plus BD times D plus AD plus BC times square root of D. And I'm back at a number that looks like this. So if I start with a number that's a plus b times square root of d, and multiply by another number that looks like c plus d times square root of d, then sort of I land back at the same thing. So in particular, like if a and b were both rational numbers, then I'd get something like expressed in the same form, where sort of like this is a new a and this is a new b, and these are again both rational numbers. or if they were both integers, again, sort of like A, B, C, and D, sorry, if A, B, C, and D were all integers or all rational numbers, then sort of the resulting things I get down here are also sort of integers or rational numbers. And so the same thing happens much simpler if you just add two things that look like this. And so what that tells you is that really sort of if I gather all the things that look like this, then that gives me a ring. So to be more precise, if I fix some D and Z, which I'm always going to take to be an integer that's not a square. So like I won't take D to be 4. I could take D to be 2, or I could take D to be 8, or I could take D to be 3, or 7, and so on. So I just don't want it to be an exact square. I could take D to be -1. Then I'm going to look at, so I'm going to write Z bracket square root of D. That just means all complex numbers of the form A plus B square root of D, where A and B are contained in Z. I'm going to write Q square root of D for all complex numbers of the form A plus B square root of D, where A and B are in Q, are our rational numbers. And then what I just justified by this computation above is the first part of this theorem, which says these are both rings. So Z square root of D and Q square root of D are rings. So they satisfy the addition and multiplication, and those sort of satisfy the expected rules. Even more is true. So it turns out that Q square root of D is a field. So if I sort of allow integer coefficients, maybe not surprising, I'm not going to get a field. But if I allow rational coefficients, then it is actually a little bit surprising that, and what's surprising here is when I'm saying Q bracket square root of D is a field, what I'm saying is that if I take like something of the form A plus B square root of D, and then I compute its reciprocal, it's also that form. So we need to verify, like we need to sort of compute things like this. So we need to like compute something like 1 over 2 plus square root of 3. So the reciprocal of 2 plus square root of 3. And we want to show we can write that as some rational number plus some rational number times square root of 3. And well, to see how we can do that, we just do sort of a standard trick for rationalizing the denominator. So let's just multiply both sides by 2 minus square root of 3, sorry, both the numerator and denominator by 2 minus square root of 3. I get on top 2 minus square root of 3. And on the bottom, I get 4 plus square root of 3 squared, so minus square root of 3 squared. And so that's going to be 2 minus square root of 3 over, well, square root of 3 squared is just 3, so over 1. Okay, so this is 2 minus square root of 3. So I got a little bit lucky. There was a 1 in the denominator there. But in general, like you're going to end up with some rational number in the denominator, or with some integer or rational number in the denominator, but that's fine. You just sort of move that up in here. So in general, sort of to prove the theorem, like if you do 1 over A plus B square root of D, this is going to be just A minus B square root of D. You multiply the bottom by A minus B square root of D as well, and you get A squared minus B squared D. Okay, and so then this is equal to A over A squared minus B squared D plus B over A squared minus B squared D times, so it's the square root of D times square root of D. Okay, and so this is where I use the fact that D wasn't a square because I need this number in the denominator to not be 0. So I should have sort of A squared minus B squared D is not 0, but it's pretty easy to see as long as D is not itself a square, this is never going to be 0. Okay, so that's how you can sort of compute reciprocals in Q squared of D, and in particular how you can show that this really is a field. Okay. So now we have some new rings. And what do we like to do with rings? Well, we like to do modular arithmetic. And this is what we talked about last time, how you can do modular arithmetic in any ring. And so in particular, we're going to do that. Well, it won't be so interesting doing q squared root of d, because that's a field, and sort of modular arithmetic is sort of never interesting in fields. But it is interesting to do it in z bracket square root of d. So just and the main example we'll look at is if we have some integer n, so like really an element of z, then we can consider sort of z squared root of d modulo n. And so here, this is just looking like z modulo n, like z mod nz, except now we also have we don't just have sort of integers, we also have sort of multiples of square root of d. And so any element in here can be represented as something of the form a plus b squared root of d, where now both a and b are in z mod nz. So in particular, there are sort of n squared elements in this ring, just from the n choices for a and the n choices for b. Okay, so example, let's say which elements are invertible in z squared of 3 modulo 7. Okay, so turns out we can do this sort of the exact same way. We can sort of do this computation the exact same way we did to show that q bracket square root of 3 was a field. So like say we have a plus b square root of 3 in sort of a, b in z mod 7z, which is f7. Okay, well, what should I do? I want to compute 1 over a plus b squared root of 3. Okay, and well, if I want to do that, let me just sort of pretend it exists. And if it does exist, then I can sort of do the same trick as before. I can multiply top by a minus b squared root of 3. And then the bottom I'll get a squared minus b squared times 3. So here I sort of multiply by a minus b squared root of 3 over a minus b squared root of 3, which is 1. So I'm just doing the standard trick we're doing before for rationalizing the denominator. Rewrite this as 3b squared, sorry. It's clear. Okay, and then this is a minus b squared root of 3 times 1 over a squared minus 3b squared. So this is going to be good. So this, like now, and so the point is a squared minus 3b squared. This is in z mod 7z. So it has an inverse as long as it's not 0. Okay. Good. So as long as this is not 0, we're in good shape and we get an inverse. So for example, of course, if a and b were both 0, then this would be 0 and we don't get an inverse, but that's fine because of course, some of the 0 element is never going to be invertible. So 0 is never invertible. We could look at sort of what happens when we get non-zero things. Well, I mean, somehow if b is 0, then we're just looking at some element in z mod 7z, and then all the non-zero ones are invertible. But it's sort of interesting to look at what happens for other ones. So like, for example, if we take 1 plus 1 square root of 3, so let's just do all of these. A squared minus 3b squared and just see what I get. Okay, so I get here, I get 1 minus 3 is minus 2, not equal to 0. So this one has an inverse. Here I get 1 minus 12. This is minus 11, which mod 7 is 3. Okay, I don't really need to do 3. The point is minus 11 is not divisible by 7, so that's not 0. If I do this, I get 1 minus 3 squared times 3, so minus 27. This is not 0 because 26 is not divisible by 7. Here I get 1 minus 64 equals minus 63. And that is equal to 0. Sorry, but I did that wrong. So that's good. Sorry. Try that again. If I'd gotten 63, that would have been 0. But I don't think I did that right. I got 1 minus 3 times 16. Okay, so that's minus 47. That's not equal to 0 because that's not divisible by 7. And I could do sorry, keep on going. So 1 minus 3 times 25, it's minus 74. That's not divisible by 7. And finally, 1 minus 3 times 36. It's 1 minus 108, so that's minus 107. And again, that's not divisible by 7. So all of these elements have inverses. Okay, and actually sort of somehow, I could always, like if I have any element, well, you can check this for any element where A is 0 has an inverse by the same thing. And then if I have any other element where A and B are both not 0, I can sort of multiply it by sort of A inverse, and I get something that looks like this. So actually, sort of, I see that everything here has an inverse. So and everything in here has an inverse. Everything non-zero has an inverse. So I've actually shown all of them. So all non-zero are invertible. So this is a field. This field sort of has 7 squared, so 49 elements, because so I have 7 choices for A and 7 choices for B. So I have 49 elements in this ring, and all non-zero ones are invertible. So in fact, this is a field with 49 elements. So this gives sort of another way to construct sort of fields of sort of larger number of elements. Okay, so we saw previously that you could do this using polynomial rings. Okay, but so when we did this computation, and also when we were computing, when we're showing that Q squared of D, that this was field, and somehow a key role was played by this rationalization of the denominator. So we multiply this by 1 over A plus B squared over 3 times A minus B squared over 3 over A minus B squared over 3. And then so the key thing was this, what you got in the denominator, this A squared minus 3B squared. Somehow, so that's an important quantity. And so we give it a name. So we define for any element in Q squared of D, so that's something in the form A plus B squared of T, where A and B are rational numbers. The norm is going to be A plus B squared of D times A minus B squared of D, which is equal to A squared minus B squared D. Okay, so this sort of takes in a quadratic, this sort of special type of quadratic rational and just spits out a rational number. Let me just point out that this quantity also appeared much earlier. Well, it tried to appear much earlier, so I wrote down the wrong thing. So this was supposed to, when I was saying the polynomial that's satisfied by a quadratic integer, a plus b squared of d, that the constant term was a squared minus b squared d. So the constant term here was the norm. Okay. Okay, so that's okay. So the norm. So this is sort of an important quantity. Was important in these previous examples. And let me just sort of codify this last example. And it really is the case that if I look at sort of z bracket square root of d mod n, so any integer n, and I look at a plus b square root of d inside of there, and that's going to be invertible if and only if the norm is coprime to n. So if this GCD of a squared minus b squared d and n is equal to 1. To show that if the norm is coprime to n, it's invertible, well, you just sort of clear the denominator, like you just rationalize the denominator, like we did in that example, and then you just need to be able to invert you need to be able to invert a squared minus b squared d, and then this is exactly, so this condition that is GCD 1 with n is exactly a condition that you can already do this in z mod nz. And then and it's not so hard to go the other direction too, but let me not discuss that. But this really gives you a way to check whether an element is invertible, and then it also gives you a way to compute. You rationalize the denominator, and then you sort of compute the inverse in z mod nz for the norm for a squared minus b squared d. Good. So you'll do lots of exercises like that on the worksheet. Let me just state a corollary related to this example. So we let r be z squared root of d. We let p be an odd prime not dividing d. Then, well, if d is not a square mod p, then the units in r modulo p is going to have p squared minus 1 elements. And so all of r mod p is p squared elements. That means this is everything except 0. So in that case, r mod p is a field. On the other hand, if d is a square mod p, you can also do the sort of similar computation using this criterion. And if you work it out, you'll find that if d is a square mod p, then r mod p cross is going to have p minus 1 squared elements. And so in particular, in that case, it will not be a field. So we'll come back to this a little bit later in the class, but this is sort of a fun example. And in particular, you see sort of exactly when you can use this construction to produce fields. So the reason we got a field in this example was because 3 is not a square mod 7. So if I work mod 7, well, then 1 squared is 1, 2 squared is 4, 3 squared is 2, 4 squared is 2, and 5 squared is 4, and 6 squared is 1. Sorry, so I never got 3 on that list of squares. So 3 is not a square mod 7, and this theorem sort of tells you that in that case we're always going to get a field, basically by the same computation. And so somehow, and the key observation is that you always can get down this case, and then the only way you can get something like you won't be able to invert this is if you get 0 here, a squared minus 3b squared, and that's sort of basically the same as saying 3 is equal to a squared over b squared. So and somehow that's saying that 3 is a square, like in that example. But since 3 is not a square, like this is never going to be 0. So let me not move this. I don't need to justify it, I think, any more than that. So let me just instead sort of do one more example. This comes up on your worksheet. So if I take d to be minus 1, then the square root of d just is square root of minus 1, which take to be I in the complex numbers. And so then sort of when I write z squared of d, really just means zi, and sort of just everything of the form a plus bi, where a and b are integers. These are called the Gaussian integers. And we'll do lots of fun things with the Gaussian integers in a little bit, but for now, it's just like any of these other examples. But anyway, the main thing here is -1 is not a square mod 3. And so by the criterion of this theorem, so here d is -1 and p is 3. So since -1 is not a square mod 3, then this quotient, and this ring of Gaussian integers modulo 3, this is a field with 9 elements in it. So this looks like a plus bi, where a and b are in z mod 3z, which is also the field with 3 elements. So, okay, this is a field with 9 elements in it. It contains, so if I just look at all the ones where b is equal to 0, so it contains the field with 3 elements in it, z mod 3z. But it's bigger, it has 9 elements. And actually, this turns out to recover the same field with 9 elements we constructed last time. So we saw before that we could construct a field with 9 elements using sort of polynomials over F3. And here, well, here we do it in sort of a different way, but we really get the same thing. So on one of your exercises, you'll write out the multiplication tables for this thing and a multiplication table for the other thing we looked at, and you'll really see that you get the same thing. Okay, but let me stop there for today, and I'll see you in class on Thursday.